Thank you. Goodbye.
Can you guys hear me and see the screen?
Yeah, I can hear you.
Okay, thank you.
I was wondering, for practicing these quantum mechanics equations, do you have any recommendation for how we should practice or study for these? Because I'm having, like, beyond the just standard questions in the homework, I'm having a hard time finding like a large number of equations to really be able to get these down well.
Right. So I won't give you tough quantum mechanics problems beyond the level of the homework. So if you're comfortable with the homework type solutions, that's the type of problems that you get in the exams also. Okay. But if you want to practice more, I mean, there's plenty of great quantum mechanics textbooks out there. One of my favorites is by David Griffiths. You know, he's written some wonderful textbooks for quantum and also for EMAG, and you can, you know, get a copy of those and then a copy of that book. There's plenty of worked out examples there, and you should, I mean, to learn the subject, but from the exam point of view, only the homework problem type problems will be given in the exam.
Okay, thank you.
Good morning.
Good morning.
Yeah. I don't know if you guys watched the Super Bowl last night. I was kind of rooting for the Kansas City Chiefs because Tom Brady's won so many, but no luck.
Yeah, half of my family was rooting for them just because why not? And then the other half was rooting for the Buccaneers because
Yeah. The Bucks haven't won many, but Tom's won so many that, yeah. And his deflate grade thing also bothers me a little bit. Anyway.
yeah, no, I didn't watch the whole thing. I just heard my mom tell me what the end and the rest of it was like.
Yeah.
Because
Total blowout. I know. Anyway, more fun stuff than the Super Bowl, quantum mechanics. Just to quickly refresh your memory, we went through the essential concepts of quantum, and the formulation is actually quite straightforward. All the information about a quantum mechanical system, such as electron moving in a semiconductor device, is contained in a complex function, psi, which has a real and an imaginary part, and it's a function in general of position, r, or x, y, z, and time. And the meaning of this wave function is, if you take the magnitude square, or psi magnitude square, which for a complex quantity can also be written as psi star psi, complex conjugate times product with the wave function itself, between position x and x plus dx, y plus dy, z plus z dz, that gives you the probability density of finding the particle in that location at that instant in time. Okay. Now, if this was electron and you have some sort of a function in space, what this tells you is, if I do the measurement once, I might have a certain probability of finding the electron at that location by squaring that quantity. Okay. If I did the experiment again, I may find a different probability of finding the particle at a different location. Okay. What it does not mean is, although the wave function is spread out in space, it does not mean that if we do the measurement, I'll measure 10% of the electron at that location, maybe 20% at that location, and so on and so forth. You cannot fracture electron. Electron itself is an indivisible particle. All that it tells you is the wave function square gives you the probability of measuring the electron at different locations in different experiments. Okay, so there's a probabilistic aspect to the description in quantum mechanics, which always bothered Albert Einstein and many other physicists from a philosophical point of view, because your gut reaction tells you that if you knew precisely the conditions of my experiment, at least in theory, I ought to be able to predict the results with absolute precision, but quantum mechanics doesn't allow you to do that. Okay. A macroscopic object can be thought of as being made up of a large number of identical copies of a quantum mechanical system, a so-called ensemble. So when you do the measurement on a macroscopic system, which is what you'd be doing in the lab, what you get is an average quantity, which is this last expression over here, of a quantity Q, whose average is given by operating on the wave function and then taking whatever the result is, you multiply by the complex conjugate, and then you integrate over all space. If the wave function wasn't normalized, normalization means adding up the probabilities over all space should give you 1. If it isn't, it's just a scaling factor, and that's what the denominator tells you, okay? And then for every quantity that I'm interested in physics, like position, momentum, energy, et cetera, you can have corresponding quantum mechanical operators, and this dictionary is given over here. And it turns out with these basic operators, you can have different combinations, and you can construct all the other relevant quantum mechanical operators. And the one that we dealt with was kinetic energy, which is p squared over 2m, okay? So you take this, you square it in terms of operators. What that means is, since grad function in 3D, or del x, if it's a one-dimensional problem, squaring that means I take the second derivative of the function, okay? So it's not del psi del x whole square, it's rather del psi del x, and then you differentiate again, and that gives you the second derivative. And by doing so, we got the famous Schrodinger equation, which is the Hamiltonian operator, which is the total energy, kinetic plus potential energy operating on the wave function, gives you the total energy operator, which we then converted into ordinary differential equations by the technique of separation of variables. And you got the time-dependent part, which is going to be the same for every quantum mechanical problem, whose solution we saw is e to the power minus j e over h bar. Now, e over h bar by the Planck relationship is omega, okay, t. So that's a time dependency for all energy eigenstates. The only difference from one problem to the other is in the space-dependent part, where this is now known as the time-independent Schrodinger equation. The starting version was called the time-dependent part. The time-independent Schrodinger equation is an eigenvalue equation, meaning that if you operate on the wave function psi, if you get the same function times a constant, which are called the eigenvalues, that's what an eigenvalue equation is, and you get eigenfunctions or eigenstates for the solutions and corresponding eigenenergies. And then you can combine the spatial part and the time-dependent part, okay? What we did that next was solve this equation for different choices of v of x. So the simplest case is if v of x is a constant, and you can set that constant potential energy to be 0 by a suitable choice of the reference potential energy. And the solution we got was a plane wave, some normalization constant a e to the power j kx minus omega t, which is a plane wave propagating in the positive x direction. You'd also get another solution, e to the power minus jkx minus omega t, which is a plane wave going in the negative x direction. All right. Was there a question? All right. So here I just choose the positive x solution, say. Then I can use my recipe for quantum mechanical expectation values and use that to calculate the momentum. And that gives you simply h bar kx, or kx is nothing but 2 pi over lambda. So that's my de Broglie relationship. Similarly, for the energy, I get energy equal to h bar omega, which turns out to be the Planck relationship, okay? Now, if you graph the energy then, so these two relationships, as I said, capture the wave-particle duality and are true for every system, electrons, protons, photons, whatever. What is different from one type of particle to the other are relationships between quantities in the first equation and the second one. So for example, between energy and momentum. So we look at the expression in the case of electrons. Energy then is given by kinetic energy, p squared over 2m, plus potential, but I've set the reference potential energy to be equal to 0. So this is a simple parabolic relationship, which is graphed over here. And I get a solution, which is h bar squared k squared over 2m. Keep this at the back of your mind because we'll be revisiting this again and again in this class. This is known as a band structure of an electron, okay? So in free space, this EK relationship or the band structure is a parabola. In a crystal, we'll see it's kind of like a parabola, but it gets to be a distorted parabola. And there's all kinds of interesting physical consequences of that. Now, in the solution of the free particle, all values of K are allowed and all values of energy are allowed, okay? The next solution that we worked out was the famous particle in a box solution, which kind of looks like the free particle, but now it's only a constant potential between 0 and L, But now I impose boundary conditions and I make the potential go to infinity at x equal to 0 and x equal to L. By solving the Schrodinger equation, once again, you could write the wave function in terms of e to the power ikx, jkx, another term e to the power minus jkx, or equivalently, by using the Euler relationship, you could write the solution in terms of sine and cosine functions, right? Because we know that e to the power jkx is some constant a sine kx plus another constant b cosine kx, and so on and so forth, right? Now, in the case of the particle in a box, instead of choosing e to the power j kx type solutions, it's more convenient to work in terms of the sine and cosine solutions. You get the same result either way. Okay, it's just that the math becomes a little bit easier to handle. So now, by applying the boundary conditions, we saw that the cosine x term has to vanish because I impose the boundary conditions that psi at 0 equals to 0 and psi at L equals to 0, because no particle can have infinite total energy. Therefore, if the potential energy goes up to infinity, the way of saying that in quantum mechanics is the probability density of finding the particles at these locations must be 0. In other words, psi 0 and psi L must be equal to 0. And that then gives you, by solving that, you get eigenstates of this form with discrete values of n, integer values, which are now allowed, and correspondingly only discrete values of energy are allowed, as given over here. Okay, so these are these discrete eigenenergies, the corresponding discrete eigenstates. To get the probability density, you have to square them. Okay, so notice that's the difference between this solution and the previous one. Here, there's no boundary condition, and it could be the way particle could be anywhere in space, and therefore all values of k or energy were allowed solutions. Okay. On the other hand, because I've applied boundary conditions, those additional boundary conditions impose restrictions on the allowed values of energy and the wave function. And that's a trend that we'll see. So imposition of boundary conditions puts restrictions on the allowed values of energy and wave functions. And that's really how the Bohr model of discrete energies was explained. Okay. Now, one interesting outgrowth of this is if I change the problem statement and say at x equal to L, I don't make the potential infinity, but make it a finite value V naught, new kinds of additional physics show up. And this is this famous quantum mechanical tunneling problem. Because now if I solve the Schrodinger equation, because the potential energy is not infinite, it's V naught, there's no reason for the wave function to vanish over here. And if you solve the Schrodinger equation, you'd find that the wave function could have a non-zero value outside of this barrier, even if the particle that I have in this box had a total energy less than the potential energy. And that's not possible classically, because for the particle with the total energy over here to get out of the box would mean that within the barrier shown by the shaded region, momentarily the particle would have to have a negative kinetic energy, because total energy equals kinetic plus potential. If my E is less than V naught, kinetic energy has to be negative, which is a nonsense in terms of classical physics, but quantum mechanics allows that. And as I said, we'll revisit this when we come to device applications. And this tunneling phenomena has both good aspects to it, but it can also be a problem. The next problem that we looked at, we didn't solve this, of course. We just sketched out the solution, is the particle in a box, but now it's not a rectangular box, but a Coulombic potential box. It's a 1/r type box, okay? Where the width of the box is not constant as in the particle in the box, but as you go to higher and higher energies, the confinement extension becomes larger and larger. So it's a wider and wider box. So now looking at the solution for the particle in a box where this width of the box L, or the width of the box L is fixed, and therefore the energy increases as n squared. Now, if the length of the box itself becomes wider, the spacing between the energies would shrink. And that's what happens in the case of energies in an atom. Okay, so as you go to higher and higher energies, the spacing doesn't increase as n squared, because the width or the length of the box is increasing at the same time. They actually get closer and closer in space. And you get a solution of the form, some bunch of constants divided by n squared, and that is your Bohr result, which led to the the entire development of quantum mechanics. Okay, and this n is now known as a principal quantum number. But then, by additional boundary conditions, one finds that you have three other quantum mechanical quantum numbers. Okay, the angular quantum number, which gives you how elliptic the orbit is, and that ranges between 0 to n-1. And for each values of these L, you can think of these electrons orbiting in these elliptical orbits as a tiny circulating electric current, which has its own magnetic moment. And this magnetic moment can point in discrete orientations with respect to an external magnetic field. The values of M then range from -L, -L-1, all the way up to +L. So you have 2L plus 1 values of that. And then finally, for each set of these quantum numbers, N, L, and M, the spin of the electron can be thought to be spinning clockwise or anti-clockwise, okay? And that gives you a magnetic moment also, which in the same units as the other angular momentum has a value of either plus or minus half, which has very interesting consequences also, as we'll see today, okay? The values of L are known as orbital quantum numbers, and that gives you an angular momentum L, h bar. And remember, the Bohr model said that the angular momentum had to be discrete integer numbers times h bar, right? And Bohr had to make that weird assumption to simply fit the experimental spectroscopic data, but quantum mechanics puts that on a more, sounder mathematical footing based on the concept of the de Broglie wave and things like that. All right. So hopefully that jogs your memory about quantum mechanics. So now with the rules of quantum, then we started applying that to different terms. Where we left off was with the periodic table, which I'm sure you've seen in your chemistry classes and many other classes. So what you do is you build up the electronic structure according to these rules of N, L, M, and S, with one additional restriction, the so-called Pauli exclusion principle, which tells you that you cannot put more than one electron in one quantum state. Now, what is a quantum state? A quantum state is a set of, in this case, a set of these numbers, N, L, M, and S, which distinguishes that quantum mechanical box, if you will, okay? So think of these values of N, L, M, and S as indices, which describe this quantum mechanical energy eigenstates, okay? And then you have to put in these electrons in these different allowed eigenstates, okay, according to the Pauli exclusion principle, okay? Now the question, of course, you might ask is, why is there an exclusion principle like that, okay? Now to understand that, what physicists realized that every particle in nature had spins S, which are either integers or half integers. Now, in the case of electrons, we just saw that the spin can be either plus or minus half, okay? On the other hand, there are other particles where the spin can be an integer number. Now, if the spin is half integer, say plus or minus half, h bar, which is what electrons are, those particles are known as fermions, after Enrico Fermi. On the other hand, if it's an integer spin, instead of being half integer, those are called bosons, after Sutcliffe-Bose, okay? And everything in nature, every fundamental particle is either half integer or integer spins, okay? And only half integer spin particles are subject to the Pauli exclusion principle, okay? Now, this point I have to tell you something about the funny behavior of what I call identical particles, okay? So what does that mean? Well, every electron in the universe is truly identical. There's no experiment that you can do to tell them apart, okay? So now if you have a scenario where instead of a single electron, say I have two electrons, okay? So suppose I have electron 1 that I put in some state A, but now I also have a second electron 2 that I put in some location B, okay? Now, what is the probability of finding the particle 1 at location A and particle 2 at location B? Well, the recipe is I have to take the square of that, right? Square magnitude of that. So it'll be psi 1 square times psi 2 square, right? So that's a joint probability distribution, okay? But now suppose I swap the positions, okay? So instead of electron 1 being at A and electron 2 at B, suppose I swap them around. So what is the joint probability in that case? So now it would be psi 1 at B times psi2 at A, right? I swap the positions. And the probability of that would be the square of that, okay? Now, if these two particles are truly identical, can I tell the two scenarios apart if I swap them? Obviously not, right? So the two probabilities of identical particles have to be the same. So I can equate the two joint probabilities, okay? Now, if I take the square roots, now, so let me take the square roots. What will I get? If I swap them, that can be the plus or -1, right? By swapping the two particles. Now, people have found that if it's half integer fermion type particles, electrons, you have to choose the negative sign. On the other hand, for bosons, you have to choose the positive sign. And the reasons for that you can't understand based on simple quantum mechanics. You have to go beyond the Schrodinger equation, use special relativity. And the guy who did that is a famous physicist known as Dirac. So you have to use the Dirac equation way, way beyond the scope of our class. Okay, we'll just take this as given, okay? So for electrons, by swapping two particles, you introduce a minus sign. Keep that at the back of your mind, okay? Now let's see if I try to put both the particles in the same state. So instead of A and B states, suppose I put the two particles in the same state. So what does this equation tell you? So psi1 is now put in A, but psi2 is also put in A, okay? And by rules of the swapping, this becomes minus psi2 at A, psi1 at A, right? Oops. See that? So I bring this over to the left-hand side. So what is psi1A or psi2A now equal to? Zero, right? That's the only possibility. So the probability of putting two fermions in the same state is zero. And that's what the Pauli exclusion principle is. On the other hand, for bosons, there's no such restriction. You can put an arbitrary number of bosons in the same state. And that also gives rise to a whole bunch of interesting physics like superconductivity and stuff like that, which of course we'll not discuss in this class. But it's interesting. People in our field of solid state electronics are starting to use some of those more exotic phenomena, such as superconductivity. So if you guys, get into R&D in this field, you'll get exciting opportunities to work not just on semiconductors, but also superconductors and things like that. Okay, so let's get back to the periodic table. And as I said, hydrogen is very straightforward. You put the first electron in the first shell, and that's the notation over here. So the first number gives you the principal quantum number N. The second number is a letter which tells you what the values of L are. And the notation in chemistry is for L equal to 0, that's called the S subshell, sharp. L equal to 1 is P, D, F, and then after that it goes alphabetically, okay? But for our purposes, we'll only stay between L equal to 0 and 1, or the S and P type shells, because by the time you build up the structure and you come to the elements of interest to us, which are things like silicon, that's all that we need, okay? The S and P type subshells, okay? So the silicon structure, the silicon atom has an atomic number of 14. The atomic number tells you the number of electrons, or equivalently the number of protons in the nucleus. The atomic mass tells you the number of protons plus the number of neutrons. Now, the proton and the neutron mass are comparable. The electron mass is negligible. So the atomic mass is the sum total of the proton and the neutral masses, while the atomic number tells you either the number of electrons in the various shells and subshells or the number of protons in the nucleus, right? So 14 electrons are put in this sort of a shell structure, okay? Now, as you build up the structure, you'll find that when the outermost shell, the so-called valence shell, has 8 electrons, all the available states are satisfied. And that is your famous rule in chemistry, that you need an outermost valence shell with a stable octet of electrons. Octet means 8, right? Now, why is that a complete valence shell? Because remember, we said that P means L equal to 1, right? So for L equal to 1, the values of M could be -1, 0, +1. So that's 3 times spin. For each of these, you could have spin plus or minus half. So you have 6 possible states. And then for the S subshell, you have 2 possible states. So 2 plus 6 gives you the stable octet of electrons. And whenever I have a complete shell like that, those elements are the so-called noble gases, such as neon, argon, and so on and so forth. Okay, helium is a special case because 2 electrons in the 1s also makes it a complete shell. Now, in the case of silicon, you see that everything up to this point is the same as neon. So people can, in a shorthand notation, write down the silicon structure as shown over here as being made up of the neon core, and then you have the outermost valence shell 3s2, 3p2. Okay, but in terms of the allowed states, we just saw that you have room for 3s2, 3p6, right? So I have a total number of 8 states available to me, but I only have 4 electrons in the case of silicon. Okay, so that then makes silicon a very unhappy element. You'd like to enter into bond formation with other silicon atoms and form covalent bonds. In fact, it forms covalent bonds with 4 other silicon atoms, as we'll see today. And that ultimately will lead to the diamond structure or the FCC unit cell with a basis of 2 atoms. So the electronic shell structure and the corresponding energies are shown schematically over here for silicon. So the first 2 go into the 1s, the next 8 go into the 2s and 2p, and then the 3s and the 3p are shown over here. Okay, but mind you, even higher than the 3s, 3p, you'd have possible states 4s, 4p, and so on and so forth. But in the case of silicon, those are unoccupied. Okay, now we'll see that the valence shell in a crystal will lead to what we now know as the valence band in a semiconductor, while the next highest available state, which does not have any electrons in them, will give rise to what's called the conduction band. So that's looking ahead. Okay, the corresponding energies are shown over here, and once again, it's a 1/r, that potential box. Okay, and you'll notice that the higher up you go in energy, the width of the box, of the confinement, becomes wider and wider, and that's why the energies get closer and closer spaced. And as you go up to higher and higher energies, you kind of asymptotically go up to what's called the vacuum level, okay, which is the reference potential energy that is set equal to 0, which is the energy that the electron would have if you yank it away from this positive nucleus and move it very, very far away where it doesn't see these attractive potentials at all. Okay, so with respect to the 0 vacuum energy, all these energies are negative. And in the case of the hydrogen atom, the ground state is minus 13.6 electron volts, the Rydberg energy. All right. Now, the other thing that I'm showing, sort of in an exaggerated fashion, is the energies between, say, n equal to 1, n equal to 2, n equal to 3, those spacings are relatively large, while the spacings between, say, the 2s and the 2p are relatively close. Okay, so the 2p is slightly more elliptic orbit than the 2s, so they're kind of close together, but all the p-type subshells will have slightly higher energies. Now, in the case of 3s and 3p, I'm showing the separation in an exaggerated fashion because I need to draw some diagrams in a second. Okay. All right. Now, then, in the last class, we looked at the shapes of these wave functions, the S-type wave functions and the P-type wave functions. And we made the comment that the S-type wave functions are spherically symmetric, okay? While the P-type wave functions have these dumbbell-type shapes with a positive and a negative lobe. So this, in this case, is a PY wave function. Similarly, you'd have a PX and a PZ and so on and so forth, okay? Each of which would have a positive lobe and a negative lobe, okay? Now, the wave functions themselves, of course, don't mean anything. You have to take the square of the wave function, okay? So if you take the square of the wave function, both the positive and the negative lobes will give you positive values, meaning that the electron probability density is high in this direction or this direction in the case of the PY type wave functions, but very low elsewhere, right? On the other hand, the S-type wave functions have equal probability density in any of these angles, theta and phi. There's only a radial dependency, as we saw in the last class. Okay. Now, what one finds is if I take the silicon atoms and I start putting them closer and closer together to make a crystal, these wave functions start overlapping in space. All right. And once they start overlapping in space, you have to construct what are known as linear combinations of atomic orbitals. Okay. Linear combinations of atomic orbitals. You may have seen this term used in your chemistry classes. Okay. What does that mean? What it means is, remember we said when we discussed quantum mechanics that actual wave function can be written as a linear combination of different values, different constants Cn times this eigenstates psi n. So you solve the problem, you get these various eigenstates, psi1, psi2, psi3, etc., etc. But then the ultimate wave function could be written as various linear combinations, so different coefficients C1, C2, C3, etc., etc. Then the analogy that we had used was if you have X, Y, Z Euclidean space, and I construct a vector V, okay, that could be written as some Vx times unit vector. So let me read it here. Suppose I have some vector V. V could be written as unit vector X times Vx plus unit vector Y times Vy plus unit vector Z times Vz, right? For different coefficients Vx, Vy, Vz. Similarly, a wave function in an infinite dimensional so-called Hilbert space can be written in terms of these basis vectors X, Y, Z. In this case, these are these eigenstates psi1, psi2, psi3, etc., for different coefficients C1, C2, C3, where the C1, C2, C3 are the analogs of this Vx, Vy, Vz. So that's sort of the correspondence. Okay. So what I'm trying to say is, in a crystal, one finds that when you put these atoms very close together, these wave functions start overlapping in space, and the total solution becomes not the discrete eigenstates by themselves, but different linear combinations of those. All right. Now I'm just going to state what these combinations are and see what the consequences are. Okay. I mean, you can solve it if you took a quantum mechanics problem and a quantum mechanics course, and actually, you can put in this potential profile for the crystal in the Schrodinger equation. You can crank the machinery on a computer, and the solutions will pop out. Okay, so let's see qualitatively what these linear combinations look like. Now, if I take an S-type orbital, which is positive everywhere, and add it to a P-type, Py-type orbital along the negative y-axis, because this is a negative sign, it cancels out. So this negative lobe becomes smaller in magnitude, while in the positive y direction, they become additive. Okay, so you get a directed orbital like this. Now, of course, to get the probability density, you have to take the square of that. So what it means is I have an electron bond, which points in this case along the positive y direction, say, and there's a tiny value of the probability in the negative y direction, and very low probabilities around the x and the y directions. Okay, so you get this directed hybridized orbitals. All right. Now let's see what that leads us to. Okay, in the actual crystal. What you'll find then is if I now construct a silicon crystal, where each silicon atom, of course, has 4 electrons in the outermost shell. We just said that silicon atoms would love to have the stable 8 electrons in the outermost shell, or the stable octet. And the way it accomplishes that is by forming 4 covalent bonds, shown by these dotted double lines, with 4 nearest neighbor silicon atoms. Okay, and by doing so, let's look at this silicon atom. It has approximately 8 electrons surrounding it, 4 of its own, and the 4 that it shares with the 4 nearest neighbors. Okay, and the way these double bonds are formed are, you have this directed sp3 hybridized orbitals that I just showed you for this silicon atom, linking up with another sp3 orbital of a neighboring silicon atom. Okay, so these 2 directed bonds link together, and that's what leads to this covalent bond formation. Now, it turns out in chemistry, there's another way by which bonds are formed also, and those are your so-called ionic bonds. And that's seen in solids where the two species, in this case, say sodium and chlorine as examples, are very, very far apart in the periodic table, such that they have very, very different electronegativities. Okay, so what does that mean? So here's the periodic table once again. So if I choose sodium, which is in column 1 of the periodic table, that means the column tells you how many electrons I have in the outermost valence shell. So clearly that is 1 electron in the outermost shell. Chlorine, on the other hand, has 7 electrons. Say sodium meets chlorine. The sodium realizes that if he simply transfers the electron completely to the chlorine, this sodium would go back to the next lower shell, which is already complete. But in the process, it becomes Na+. Chlorine was at 7. It's just 1 short of the magic 8. So if it adds that electron, it becomes a chlorine minus. Now, of course, you remember that unlike charges attract each other. So the sodium ion has Coulombic attractions with the chlorine ion, and that leads to the formation of sodium chloride with strong ionic bonds. Okay, and that, of course, is common salt. Now, these are the two extreme limits, ionic bond or a purely covalent bond. In other solids, you can have something in between, which is partly ionic and partly covalent in nature. So once again, let's go back to the periodic table and look at another compound semiconductor, such as gallium arsenide or aluminum arsenide. Okay, or I guess I don't show the gallium and the arsenic over here. So let's look at something analogous. Gallium is in column 3 of the periodic table, just like aluminum. Arsenic is in column 5 of the periodic table, just like phosphorus. So gallium would be somewhere down here, arsenic somewhere down over there. Let's just illustrate that in the case of aluminum phosphide, same physics. Okay, now aluminum in column 3 and phosphorus in column 5 tend to form a bond which is partly covalent but also partly ionic in character, because just like the sodium electron shifted over to the chlorine, the electrons in aluminum would tend to shift over to the phosphorus. So aluminum becomes slightly positively charged, but it doesn't transfer over completely. And the phosphorus becomes slightly negatively charged. So that gives you the ionic component of the bonding, while because it's not completely transferred, you also share the electrons between the aluminum and the phosphorus. So aluminum phosphide or gallium arsenide, they are partly ionic, partly covalent in nature. Okay. All right. Now there's other kinds of bonds also, which are called molecular bonds due to what are called van der Waals interactions, or metallic bonds in metals like sodium, but those are not relevant for our purposes. Okay. Any questions? All right. So the next thing that I'm interested in doing is trying to figure out what happens to these distinct eigenenergies in an isolated atom. And then when I bring these atoms together to form a crystal. Okay. So the punchline is the discrete atomic energy levels in an atom will split up into a multitude of energies in a crystal. And in a crystal, since I have a large number of atoms that I bring together, these multitude of energies will form what's called a continuous band of allowed energy states. So that's going to be the answer. So let's see how we get there. Okay. Now to make our picture simple, instead of looking at a crystal with a huge number of atoms that are brought together, where all these wave functions overlap and so on and so forth, let's look at a simple case of 2 atoms brought together. Let's see what the consequence of that is. Okay. And this is sort of a thought process of maybe making a hydrogen molecule, if you will. Okay. So I have a hydrogen atom over here, another hydrogen atom over here, each with its own wave function. All right. And initially, these 2 hydrogen atoms are very, very far apart. Okay. And I'm qualitatively drawing a wave function which is kind of high near the nucleus itself. And then as you get farther away, suppose these are S-type orbitals, we saw that they kind of exponentially die down. Okay. Now, if this hydrogen atom was kept in Austin and this hydrogen atom was kept in Dallas, although in principle these wave functions extend to plus or minus infinity, the actual overlap of those wave functions for a hydrogen atom in Austin and a hydrogen atom in Dallas is obviously negligible, right? So you can think of them as essentially isolated hydrogen atoms, and it's two separate hydrogen atom problems. Okay, so I have this 1 over R type Coulombic potential, and you get the solution, either the Bohr model or the more accurate quantum mechanical model, and you get these discrete states which are identical. Okay, now you bring these atoms closer and closer together so that you start having some finite overlap of these wave functions in space. All right. Now, once you do that, as we just mentioned in the previous slide, the actual solutions of the two hydrogen atom problem would be discrete linear combinations of these atomic orbitals. Okay, and you have to find out how many distinct linear combinations are possible. Then in the case of two wave functions like this, one finds that there's only two possibilities. You can simply add up the two, psi1 plus psi2, as shown over here, or you take the difference, psi1 minus psi2. Those are the only two distinct possibilities as shown over here. Now you might say at this point, no, I mean, I'd see two other possibilities, right? I could have both of these negative, or I could flip them. This could be negative and that could be positive, right? But remember, the physical meaning is you have to take the square of the wave function, right? So if I take this and I square this, do I get the same or a different probability density than if I squared this? Anybody?
It's the same.
Same. Similarly, this is a so-called anti-symmetric or anti-bonding orbital. The lower one is a symmetric case. If I squared this versus I squared this, same or different? Same, right? So you'll see that's true not only for this two atom case, it'll be true for any number of atoms. Okay, you have all these combinations, but keeping in mind that you have to ultimately square them, you'll find that for two atoms, there's only two distinct possibilities. For n atoms, there'll be only n distinct linear combinations, keeping in mind the squaring business. Okay, and of course, in a crystal, this n is going to be huge, of the order of the Avogadro number. Okay, 6 times 10 to the 23 per unit per gram mole and things like that. Okay, so that's what you'll have in an actual crystal. Now let's see what ends up happening if I take these linear combinations to these distinct atomic energies. I claim that they'll split up in the case of two atoms into two energy levels, a lower energy level corresponding with the bonding case and a higher energy level corresponding with the anti-bonding case. Okay, now let's see physically why that is. Now, if I bring these two nuclei together, remember there's a positive nucleus here, positive nucleus over there, okay? And initially, they had this 1 over R type Coulombic potential, right? But if I bring two of these nuclei close together, the net potential profile is given by this black curve over here, okay? The individual ones are given by this black and this dotted lines, but if you bring them together, in the middle, there's a lowering of the potential as shown by this black line. And that's a key point to understand. Now, why is there a lowering of the potential? Well, think of an electron over here, an electron over there. Now, if it was an isolated atom, this electron could only be attracted by this nucleus, right? But now, because there's another nucleus in the near vicinity, this electron is attracted not only by this nucleus, is also attracted by this, right? So there's a net lowering of the potential energy when I have two positive nuclei which can attract that electron. Same for the other electron. Okay, so there's a net lowering of this potential energy between the two nuclei. Does everybody see that? That's a key point. Okay, so then if I see...
Wait, so is it that if they're both negative, it's lowering?
No, it both unlike. It's an attractive force if it's different charges, right? So I'm looking at the attraction between the negative electron and the positive nucleus. The nuclei themselves are repelling each other, right? But I'm interested in the attractive force between the negative electron and the positive nucleus, right? And I'm saying that if I have two of these nucleus attracting this electron, that's more of an attraction than a single nucleus attracting it in this region, right? But the nuclei themselves are pushing themselves apart, and that will be important also. But right now I'm looking at the attractive potential between the electron and the nucleus. Is that okay?
Yeah, I think I'm just a little bit confused on what the VR graph is actually of. Like what?
This VR graph is the attractive Coulombic potential of two electrons with now two nuclei.
Oh, okay. So the center point is like closer to one or closer to the other.
Right.
Okay.
So I'm not including the repulsion between the nuclei or the repulsion between the electrons. That'll come later on. I'm just looking at now the attraction between the electrons and the nuclei. Okay. All right. So now that I see that there's a net lowering of the potential between in the region between the two nuclei, let's see what impact it has on the linear combinations, the symmetric or the even combination versus the anti-symmetric odd combination. Okay. So for the symmetric combination, I see that I have a large wave function probability density between the nuclei, right? So between the nuclei, I have a large electron cloud, right? In the case of the bonding orbital. So that leads to a lowering of the energy. On the other hand, for the anti-bonding case, what is the probability density of finding electrons in between the nuclei? Right at the center point, the probability density is anybody? So it crosses through 0. Therefore, right at this point, the probability is?
At which point? I can't see where your mouse is. So.
Oh, I see. Okay, so I'm looking at the anti-bonding linear combination, and I'm looking at the midpoint where it crosses the horizontal line. I guess you can't see
zero, right?
It'll be 0, right? Because you have to square it, okay? So there's not going to be any lowering of the energy in the case of the anti-bonding orbital, okay? In fact, there'll be a net increase of the energy because remember we said that there's these repulsive forces between these three nuclei and things like that, and between the electrons themselves. And basically for the anti-bonding case, there's a net increase of the energy, while in the bonding case, because I have high probability density between the nuclei where there was a lowering of the potential, there's a reduction of the energy. Okay. Now, another factor which causes this energy to increase for the anti-bonding case is because the anti-bonding solution has more wiggles and bends to it. Okay. And you'll find in quantum mechanics that a wave function which is more gently varying versus a wave function which varies a lot, this will have a higher kinetic energy. Why is that? Well, remember the kinetic energy is in terms of p squared over 2m, where the momentum operator is given by h bar over j, h bar over j, del x, right? So what it tells you is a wave function which has a lot of variations of the slope, so that when I operate that by del x, we'll have a larger momentum and therefore a larger kinetic energy than a wave function which is more gently varying in space. A wave function which has more wiggles, if you operate on that by this momentum operator and then you square the thing, we'll have a larger kinetic energy. Okay, so qualitatively, that's also why the anti-symmetric case will have a larger energy than the more gently varying symmetric case. Okay. All right. So for two atoms, I get two separate energy levels. Okay. Now the separation of the energies is going to be a function of how much the overlap of the wave functions is, not the number of atoms. Okay. That's a key distinction. So if these two atoms, as I said, were in Austin and Dallas, the overlap of the wave functions is negligible, and these converge back to these discrete atomic energy levels. If I bring both to Austin, and not just that, if I both bring them to the ER building, the overlap is going to be even larger, the separation will be even larger. Okay, so the separation depends on the separation between the separation in energy depends on the separation in space. Okay, so what it tells me is if I have a crystal where the distance between the atoms or the lattice constant is very large, very small, the separation of these energy levels in the band is going to be large. On the other hand, if the lattice constant is very large, the energy band width is going to be relatively small. Okay. Now, the number of states that I have does depend on the number of atoms. So in the case of two atoms, I have two states. If I have an Avogadro number of atoms, I'll have an Avogadro number of states. And since the Avogadro number is a very large number, in a crystal, this will essentially form a continuum of energies. And that's why it's called the band of allowed energy. Okay. So that's what I'm showing in the next slide. Okay, so now let's look at, say, a toy model of silicon, okay, where I'm plotting the energy as a function of the separation between the atoms. So this is separation between the atoms. Okay, so on the right-hand side, these atoms are very, very far apart, and I'm considering n atoms of crystal, of the silicon atom, where n would be of the order of the Avogadro number, huge number, 6 times 10 to the 23. If I looked at a gram mole of silicon, if it's smaller than that, it'd be a smaller number, but something of the order of 6 times 10 to the 23 per unit. Something of the order of 6 times 10 to the 23 in the device or the silicon wafer. So it's very, very large number, okay? Initially, they're very, very far apart. Like I said, you get this discrete atomic energy levels of silicon. So I have the 1s state, 2s, 2p, and then the valence shell, which is the one that I'm interested in. That's my valence shell. And that will lead to a band of energies known as a valence band. Then higher than that, you have the 4s, 4p, and so on and so forth. These are unoccupied, and they'll give rise to the conduction band in the next slide, okay? All right, so I bring these atoms closer and closer together by moving to the left, all right? And as I do so, these wave functions of silicon electrons start overlapping more and more, and this discrete atomic energy levels in silicon start spreading out, and they spread out more in energy the closer the overlap, okay? So that's what I'm showing. So as I move to the left, these energies start separating out. And because now I'm looking at a huge number of atoms, n, I get n energy levels, and they're so close in space that it's almost like a continuous band of energies. But if I looked with enough energy precision, I'd get discrete energy levels, n discrete energy levels, okay? But they're basically a continuum, okay? Now in the 3s, I have 2 electrons, 2 states. Therefore, the 2n available states in the 3s orbital are occupied by the 2n electrons now. On the other hand, for the 3p, we saw that we have 6 available states, but I only have 2 in the case of silicon, right? So I have 6n available states in the 3p orbital, only 2n of those are occupied, all right? I bring the atoms closer and closer together, that spreads out, and there comes a point where this 3s and the 3p energies kind of merge together. So that's the point I get this s and 3p hybridization. What the term hybridization means is these wave functions lose their distinct S-type shape or P-type shape, and you take linear combinations as I described over here. So that turns out to be a better description of this composite wave functions, all right? Now, of course, I'm telling you stuff without proving many of these things. To prove them, you have to ultimately, put this very, very complicated periodic crystalline potential in the Schrodinger equation, and you solve it. Clearly, that's a non-trivial task, even with a computer, but that's what you do, if you take a graduate course in quantum mechanics or solid state physics and so on and so forth. But hopefully you see qualitatively how these are coming about, okay? All right, so I get this hybridization, and I keep going. The energies start separating out, and at some point, something very, very funny happens. You get a set of energies which keep going down in energy, and a set of energies which keep moving up in energy. That's what you saw over here, right? But then one finds that if I count the number of states that are available to me and the number of electrons that I have a strange situation, because I have 2n plus 6n or 8n states available to me in this 3s and the 3p orbitals, but I only have 2n plus 2n, 4n electrons. I have 8n states, half of which go down in energy, half of which move up in energy, and 4n electrons that I need to fit in. Now, from the energy point of view, of course, if I have 4n lower energy states, I might as well put all 4n of the electrons into those available states, and that gives rise to this filled up valence band. And the higher lying 4n states are going to be empty, and that gives rise to the conduction band. Okay. Now, even higher than that, you have the 4s, 4p, and so on and so forth. these would actually give bands that are totally empty above the conduction band. Okay. Now let's go to the lower energies. Let's see what happens there. Okay. So you find that the 3s, 2s, and the 2p, those stay as distinct, more or less distinct atomic energy levels, but then at even closer spacing, they start spreading out. While the 1s, at this point at least, there's hardly any spreading out at all. Now let me ask you, why do you think that is qualitatively? Why is there more of a separation of these energy states for the 3s, 3p than for the 2s, 2p? Any guesses?
Do you not have to go to another shell if you have a 3s, 3p instead of 2s?
No. Which wave functions do you think spread out more in space? The third orbital or the second orbital?
Third orbital.
Third, like it has to go one more out, so it's a bigger
Right.
area, I thought. But
So in which case do you think you'd have a greater overlap, spatial overlap of the wave functions? For the third orbital or the second orbital?
The second.
No,
Yeah,
the overlap
the
between neighboring atoms. The 2s orbitals are more closely localized around the nuclei, right? The 3s, that's a valence shell, that's the outerlying orbitals, okay? So when I bring two silicon atoms together, the 3s orbitals would start overlapping earlier than the 2s orbitals, right? Because the 2s orbitals are, kind of highly localized around the nuclei. Similarly, the 1s is even more localized. So the bottom line is these core shells hardly spread out at all. It's a valence shell that spreads out in energy the most, okay? And furthermore, the 1s and the 2s, 2p, they have as many electrons as states in them. So all of these constitute this neon core that I mentioned. And from a chemistry point of view or semiconductor physics point of view, that hardly plays any role at all. All the fun stuff is in the outermost shell from a semiconductor physics or a chemistry point of view. All right.
if the 2s are smaller though, why would they not overlap more than the 3s?
No, because I'm looking at the overlap between neighboring atoms, right? So I have a silicon atom with its say 2s, 2p, okay? Neighboring silicon atom, 2s, 2p. But then I have the 3s, 3p, which is more spread out, 3s, 3p, right? So when I bring the silicon atoms closer together, you notice that the 3s, 3ps are the ones that overlap first, right? The 2s, 2p, they're not as spread out, so therefore they don't spread out as much. The 1s's are even more localized, right? So on this scale, I'm showing that the 1s levels are not spreading out at all. Okay. And once again, the amount of spreading out depends on how much spatial overlap there was between the wave functions. More overlap, more spreading out. All right. Now, if I keep going, you'll find that ultimately these energy levels all start going up. And that goes back to the question that someone had raised earlier on about what happens to these nuclei in terms of their potential energy. If you get them closer and closer together still, the repulsion between the nuclei or the repulsion between the electrons starts playing a greater and greater role, and that's what causes the energy to ultimately start increasing, okay? So what happens is in this crystal, it'll settle at a separation where the total energy is going to be minimum, okay? And that separation determines what we call the lattice constant A, okay? So you have, for this whole ensemble of atoms in the crystal, you look at the minimum energy configuration, and that gives you the lattice constant, and that's what it's settled on, okay? So you can think of these atoms as being kind of connected by these imaginary springs, okay? These are these interatomic forces or interatomic potentials, and they'll settle in a configuration where the springs are relaxed, okay? If you try to bring these closer together, these atoms closer together, it's kind of like compressing the springs. And if you let it go, it'll move this way. On the other hand, if I try to pull these atoms farther apart, it's like extending the springs, okay? And if you let it go, it'll relax back again, okay? And of course, the spring, if I move these atoms from their equilibrium position, the springs will start vibrating. And those vibrations are called phonons that we'll discuss later on in chapter 3, okay? these collective vibrations of the atoms. They're basically like sound waves propagating in the crystal. Very, very important because they can cause scattering of electrons, as we'll discuss in chapter 3. Everybody with me?
Yeah.
Okay. So to summarize then, starting from the discrete atomic energy levels, as you start bringing them closer together and the valence wave functions start overlapping, these discrete energy levels spread out more and more as the overlap becomes more and more. And then if you have a large number of atoms, that leads to essentially a continuum of energies in energy bands separated by forbidden energy gaps. Okay. So in the case of silicon, that energy gap is 1.1 electron volts. Right. Now I realize the first time you meet these concepts, it's hard to grasp. Okay. So it takes a while to get comfortable with it. Okay. And I've been teaching this class for what? God, more than 30 years. Depressing. And even now, I sometimes get confused. So, I mean, if you're confused, that means you're on the right track. If everything makes perfect sense from the get-go, maybe you haven't quite understood all the intricacies. Okay. So it's perfectly okay to be initially confused by quantum mechanics. But, once you think about it, hopefully it becomes more and more physically meaningful. All right. So now let's look at a cartoon model of a finite crystal, where what I'm showing are these nuclei shown by these positive charges. Okay, this could be the silicon nuclei. And then I have these discrete atomic energy levels to begin with in this 1/r type Coulombic potentials. Okay. And as I said, if you bring these atoms close enough, this discrete energy levels start spreading out, okay, into essentially bands of energies. The higher lying states, the wave functions overlap more. Therefore, they spread out more in energy. The lower lying core states don't spread out as much. All these core levels are boring for us. All the fun stuff is in the highest, almost completely occupied valence band. And then you have a forbidden energy gap at the next set of states, which is going to be almost completely empty. It's called the conduction band. But even above that, you have totally empty states, ultimately leading to a continuum, which I set equal to the reference potential energy of 0, and that's called the vacuum level. Okay. The energy it takes to yank electron out of the solid in the valence band into the vacuum level is called your ionization energy. Okay. And if I give these electrons enough energy to come out, that's the photoelectric effect that we talked about in chapter 2. Okay. So what we find is you can think of this problem of a crystal as a particle in a box, except that it's not a rectangular box, but sort of a Coulombic 1/r type box. But really, we have two types of boxes that we're talking about, okay? What does that mean? Well, first of all, you have the atomic boxes, the 1/r type potentials that I've been yapping about, right? And you get these energy levels. But then if you have a finite crystal of length L, you can think of this finite crystal length as another box, right? Bounded by this vacuum level that I talked about. Okay, so it's tiny boxes made up by these atomic nuclei enclosed within a larger box, which is the finite length of the crystal itself. All right. So remember we said that anytime I put a particle in a box, all values of K are no longer allowed, but you only have distinct values of K that are allowed, right? So that gives you these discrete eigenenergies in a sign, KNX, and then you have these discrete energies. If you look at the particle in a box solution, you get discrete eigenenergies which scale as n squared in the case of a rectangular box, or has 1/n² dependency in the case of atomic boxes as conceived by Bohr and things like that. Okay. Similarly, when I put a particle in this entire crystal box, that also will only allow you to have distinct values of these wave vectors K and the corresponding energies, h⁻², k² over 2m. Okay. We'll see that when you count the number of available states in a crystal. Does that make sense? Or is that kind of confusing? All right, so we'll come back to this, in chapter 3 when you start counting quantum states, giving you what's called the density of states and things like that. So this is meant to be a preview of that. Okay. All right. So now let's just focus on the valence band and the conduction band and not worry about the core levels any further. Okay. That's what I'm showing down below. So that's my valence band, which is almost completely full of energy, full of electrons, and the conduction band, which is almost completely empty, separated by, which is called the energy gap. Okay. Now it's important that you understand these so-called simplified band diagrams very, 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 very well, because I'm telling you up front, I will give you problems in the midterm and the final where you have to analyze band diagrams like this. And every single device that we'll analyze will be in terms of energy band diagrams. I'll have also given you homework problems. So understanding simplified energy band diagrams is absolutely key to understanding this course, okay? So I'll keep hammering this concept again and again and again. So let's see what the axes are in this diagram, okay? What do you think is the horizontal axis? In these diagrams, what is this axis?
Just the x-axis?
X-axis or position, right? Distance. Yeah, you can call it x-axis, okay?
Are the pluses where the nucleus is, or
Yes.
are they just?
Yeah, the pluses are the nucleuses, yeah. And they're positive because they have the protons. And the neutrons, but the neutrons, of course, have no charge, okay? So the horizontal axis is position in the device, right? What is the vertical axis? It is electron energy increasing upwards, okay? Now, of course, energy has two parts, kinetic plus potential, okay? If the electron is at this point, the potential, the kinetic energy is 0 at this point. It only has potential energy. But if I move up in the band, I'm adding more and more kinetic energy to the particle. So at the band edge, it's only potential energy. And as I move up, I add kinetic energy to the electron, okay? So these energy band diagrams are electron energy increasing upwards as a function of position in the semiconductor, okay? Holes that I have introduced in chapter 1 very briefly, and I'm going to revisit in a second, are missing states. And for holes in the valence band, so if I yank electron out of the valence band and put it into the conduction band, that's called a conduction electron. And what's left behind, we'll see, will behave like a positively charged particle. And for holes at the top of the valence band EV, they have only potential energy, but hole kinetic energy will increase downward. So electron kinetic energy increases upward, hole kinetic energy increases downward. And you can understand that easily using this analogy of water droplets and air bubbles that I mentioned before. Let me show that and then we'll come back to this again. So you can think of this empty conduction band as an empty water bottle and the full valence band as a bottle full of water. And as I mentioned in chapter 1, if I take this empty bottle and I move it around in the gravitational field, there's obviously no net transport of water from one end to the other because there's no water in there at all, right? Similarly, for a full valence band, although some water could move from one end of the bottle to the other, it has to dislodge other water molecules and there'll be no net transport of water. Similarly, a completely full valence band cannot give rise to any electrical conduction, okay? Which is kind of a little bit hard to understand at first, okay? And that boils down to the Pauli exclusion principle, right? Because if electron was to gain energy from external electric field, this state already has electron in it, so that has to move down, and this whole ensemble cannot gain any net energy. So in the case of these water molecules, it's not really the Pauli principle, but it's kind of like the analog of the Pauli principle, because if I dislodge water molecules, there's already a water molecule there, right? Two water molecules can be squashed into the same region in space. So it's kind of like the analog of the Pauli principle, but it isn't really the Pauli principle, okay? So, I mean, don't carry analogies too far. Now, let's look at the right-hand side. So we said that you could take a few electrons from the full valence band into the conduction band, and that creates negatively charged conduction electrons, and what's left behind behave like positively charged states called holes. And the analogy that we introduced in chapter 1 is, you can think of this as water droplets that were introduced in this empty bottle, which move downwards in gravity. and what's left behind are air bubbles, which move up, right? So the energy of the electron, of the droplets and the bubbles are in opposite directions. Similarly for the electrons and the holes, and they move in opposite directions. If I apply electric field, one finds that the positive holes will move in the direction of the electric field, but the electrons with a negative charge will move opposite to the electric field. All right. So coming to this band diagram, simple band diagram, we see that in this case, I'm showing that the potential energy is constant everywhere, right? Because the bands are flat. Now, what is the potential energy of electron equal to? Potential energy is equal to the charge of the electron, which is minus Q, minus 1.6 times 10 to the power minus 19 coulombs, times electrostatic potential. That's your potential energy, right? Electrostatic potential energy. Now, if my potential energy as shown is constant, what am I saying about the value of the electrostatic potential as a function of position? It's constant also, right? Now, how is electrostatic potential related to electric field? You saw that in 302, and hopefully you've taken 325. Electric field is given by minus dV dx. Remember that? It's minus the gradient of the electrostatic potential. So the fact that I'm showing the bands flat, meaning that the potential energy is constant everywhere, tells you that the electrostatic potential is constant. So what is my electric field in this case? Anybody?
0, since there's no change.
Very good. If you take the gradient of a constant, it's 0. So this is the band diagram for a 0 electric field. Now, what do you think would happen if I had electric field? How would the band diagrams change? Well, if I had electric field, the bands would slope. Okay. Now, moving on, to make this diagram simpler, generally people don't show the entire band. You just show the bottom of the conduction band, which is shown as EC, and the top of the valence band. And what's implicit is they will line parallel to that, corresponding to the width of this band, a line parallel to that. Okay. Generally speaking, you don't show the top of that and the bottom of this. I just plot EC and EV as a function of position. Okay, so that's what I'm drawing over here. EC and EV as a function of position, and the separation between that is called the energy gap. Okay. In this case, I'm seeing that there's a slope, right? Therefore, I have a non-zero electric field. But is my electric field varying or constant in a scenario like this?
Should be constant.
Constant.
Should be constant.
With
Very
the
good.
linear
Because
change.
exactly, because it's a constant slope. Okay. On the other hand, in a PN junction, we'll see that the band diagrams will look like this. You may have seen this in 302, maybe, I don't know, or 438. So EC, EV now have spatially dependent varying electric field. So here the electric field is 0, electric field gradually increases and then becomes 0 again. Okay. So the key point is, in all these diagrams, electron energy increases upward. If I'm at the minimum of the band, that's only potential energy. And as I move up, I add kinetic energy to the system. Similarly, over here, I have whole potential energy. As I add whole kinetic energy, I move down in this band. And they've been plotted as a function of energy. So, like I said, I cannot overemphasize the importance of this energy band diagram. So we'll keep looking at it again and again and again. All right. Now, before I leave this, I want to point out one other thing, and that is another way of drawing energy bands. But here, you plot the energy not as a function of position, but as a function of the wave vector k. And this is something that we had derived in the last class, and I pointed out, okay? So we had said, remember that kinetic energy equals p squared over 2m, and p is equal to h bar k, so that worked out to h bar squared k squared over 2m. So if I plot E as a function of k is the wave vector, k equals 2 pi over the de Broglie wavelength, okay? And h bar k is momentum, that's the de Broglie relationship, okay? So E equal to p squared over 2m works out to h bar squared k squared over 2m, which is, of course, a parabola, okay? This parabola, at this point, k equal to 0, how much kinetic energy does that electron have? If k equals 0, the momentum equals 0, therefore the kinetic energy is 0, obviously, right? Therefore, at that point, it only has potential energy. So that point corresponds to EC. As I add kinetic energy, in the simplified diagram, I move up in energy. In this EK diagram, I'm moving up in energy. In between, I have the energy gap, forbidden states. Here, this point corresponds to EV. For electrons, the energy decreases downward, but if I use the language of holes, the whole energy increases downward. Okay, so that's the correspondence. Now, these band EK diagrams are called band structure or dispersion relationship. And they're correlated with this so-called simplified band diagrams, where I plot energies as a function of position. Now, although both forms of these diagrams are important, in this class, we'll be primarily dealing with the simplified band diagrams, energy as a function of position. Only once in a while, I look at energies as a function of K, which is basically proportional to the momentum or the velocity. All right, I will use that once in a while to especially look at optical properties, but this is especially important. This one important, but not quite as much for our class. On the other hand, I know you guys are absolutely loving 339, so I'm sure all of you will major in solid state electronics and you'll take graduate courses. So in a graduate class, you'll see a lot of these EK diagrams. Okay. Now, these band gaps that I mentioned are a nice way of distinguishing between all categories of solids, insulators, conductors such as metals, and something in between, which is semiconductors. And this is something that we introduced in chapter 1, and that is you can distinguish between these classes of solids in terms of the electrical resistivities or conductivities, simply in terms of the magnitude of this energy band gap. If the energy gap is very, very large, you end up getting an insulator, because now these electrons in the full valence band simply can't get up into the conduction band. Okay, so the valence band is full, cannot give rise to an electrical conduction because of the Pauli principle. The conduction band is empty. Obviously, there will be no transport of electrons in electric field. On the other hand, a metal has a zero band gap, and it could be zero either by having a band which is partially full, or by having the valence band overlap in energy with the conduction band. So basically, I have available states just higher than the highest lying states over here, either in this case or in this case. So now if I apply electric field, the electrons could very easily gain kinetic energy and move up in energy, because I have available states right above the full states. Okay, and that's what makes a metal such an excellent conductor. On the other hand, the semiconductor has a modest band gap. What's modest? Energy gaps of the order of 1 electron volt or so is what makes it a semiconductor, because now you have to compare that with what I call the thermal energy of the system, KT. K is the Boltzmann constant, T is temperature in Kelvin, and that at room temperature is approximately 25 milli-electron volts. We'll see that gives you the probability of thermally exciting carriers from the valence to the conduction band. And these gaps are modest. You have a few electrons that are excited, giving you negatively charged conduction electrons. And what's left behind are these positive holes. Okay, and that's this analogy that we had over here. So on Wednesday, that's what we'll start off with this concept of holes, which I'm claiming behave as positively charged carriers. And we'll prove that using the EK diagram, the band structure, the dispersion relationship. Okay, and that's where we'll start off with. And we'll find that these band structures introduce some really funky concepts. Not only this idea of positive holes, but you have electrons in the valence band with a negative mass. So really, really interesting Star Trek-y type concepts. All right. Any questions? All right. See you on Wednesday.
Thank you.
Thank you.
Mhm.